Today we're going to talk about mixtures of different chemicals or components in the environment and how to approach them. What is a mixture? A mixture can be different things. For example, it can be a substance that on its own is already a mixture. For example, UV light. You cannot distinguish between UVA, UVC and UVB. Products that contain more than one chemical are also mixtures. For example, the cosmetic that you put on your face this morning is composed of different chemical products. Chemicals jointly emitted together from a production site can be a mixture that could be a risk to the environment. On production sites, sometimes you have different industries that all put their chemicals into the environment, and as such, the environment can be polluted or can get polluted by different mixtures at the same time. As a field example, everybody knows that on the 11th of March 2011, a disastrous earthquake and tsunami hit the Japanese coast. As a follow-up of that, the Fukushima nuclear power plant was hit, but alongside this nuclear power plant, more than 130 other chemical industries were hit as well, and a lot of chemicals were jointly emitted to the environment. As such, we are now facing not only a radiological but also a chemical risk. So how to approach them? You can directly test the mixture of concern by getting a field sample and quantify the total toxic impact. On the other hand, you can try to identify the different components in your mixture in a top-down approach, for example by doing a toxic identification evaluation. But another way is a bottom-up approach, where you first identify the different components of your mixture and then try to predict its complete effect. In the rest of this presentation, we will be focusing on bottom-up approaches or component-based approaches. The basic information you need for such a component-based approach is knowledge on the different components of your mixture and know or test the dose-effect relationship. A dose-effect curve looks like the one that you see on the screen, where on the y-axis you have the effect and on the x-axis you have the concentration. Typically it gives, for example, a sigmoidal curve showing, for example, growth inhibition. Two basic models can then be applied to these different components to predict the mixture, the total mixture response. It is concentration addition and independent action. Concentration addition assumes that your components in your mixture have the same mode of action or the same site of action. So they have a different potency, but you can substitute one chemical by the other. An example to illustrate it to you is a sham experiment, where you have two potions of the same toxic component, and you put half of one together with half of the other one. So you have in the EC50 concentration, and you still have 50% effect in your final product. So you work in concentration addition with effect concentrations. The other approach is independent action. The assumption for independent action is that your components have the same endpoint, but a different mode of action. And there is no interaction between them. For example, if you have 100 plants and one substance kills 50% of these plants in one way, and the other one kills 50% of the plants in the other way, you will end up with 25% of your plants surviving. So in independent action, you will be multiplying effects. If you look at it more mathematically, you end up with these two equations. The top one for independent action, where you will be multiplying the effects, and the down one with for concentration addition, where you will be summing up effect concentrations. So I hope that with this smart movie you learned a little bit on how to approach mixture toxicity in the environment.